Hey everyone, and welcome back to the channel. We are back to another systems design video after a brief hiatus last week to go talk with Stefan. I won't lie, it is a slightly disappointing feeling to spend like 8 hours a week making systems design videos, only to spend about 30 minutes a week, metaphorically just like pooping on camera to make a video with Stefan and then seeing it get 4 times the views as my normal videos. But that's okay, we push onwards. For those of you who are very attracted by L7 titles in videos, from now on I should let it be known that I am an L7 Rizlord, and please watch all of these systems design videos. So without further ado, let's talk about building some video games. Okay, let's start over because my pencil was not working. So if you weren't looking at the title very much, what we're going to be building in this game is something like Fortnite, COD Warzone, PUBG, any of those types of games where basically you've got a bunch of different players in a big 2D playing field, and then as the game progresses, we've got some sort of zone and it's gradually closing in on you. So the area that you're allowed to be in as an alive player is gradually decreasing. You've got a bunch of people that start out in this lobby, and the number of players actively in the game begins decreasing. So, for example, let's imagine me and Tech Lead are in this zone. As you can see, I've absolutely sniped him across the zone right there. Good job, Jordan. So even though this is mainly for one of these Battle Royale games, it can really apply to any video game where there's going to be movement and, like a massive 2D zone where the players can occupy any part of that. It's going to be less significant for something like Rocket League, for example, where there's only 6 people in a game and it's a pretty small playing field. But if we're talking about like World of Warcraft or something where there can potentially be a lot of different players on a server, or Minecraft, this could potentially be useful there. So let's go through some formal problem requirements. Basically, like I mentioned, we're building a Battle Royale game. We've got a bunch of players who can move around. They can interact with a bunch of stateful items where the stateful items are not necessarily playable. So for example, in PUBG, you can drive around in a car, you can drop things, you can pick them up, you can open doors, things like that. Cool. Additionally, in a given lobby, let's say we can have up to 1,000 players. So ideally, we can get a lot of load on our server, and this problem isn't too easy for us. Additionally, let's imagine there are tens of thousands of additional items, right? If this is PUBG, like literally every single door can be opened. There are all of these just like random chests and stuff that can be looted. There's actually a ton of basically items that you have to keep track of state for. If it's Fortnite, pretty much every building that you build is adding state to the game server because everyone has to know that that thing was built. Cool. And then also we should be able to support pings of like 10 millis. So if you have a ping of 10, it basically means every 10 milliseconds you're hearing from the server, and you're probably sending stuff to the server as well. So that's 100 times per second per user. So we really have to make this thing fast. We're probably going to want to be storing everything in memory, and we'll talk about that more in a little bit. Cool. So the first thing that we're going to do is talk about at a very high level. Let's say I'm a game client, right? I'm playing on my laptop over here, and I'm trying to communicate my game state updates, right? Because now I have to basically tell everyone else who's playing the video game what it is that I'm doing. So what's one way that I could do that? Well, for starters, I could send them the exact keystrokes that I'm pressing, right? So that's easy because at the end of the day, it's just one letter that I'm pressing at a time, or maybe a mouse click or something like that. But at the same time, this is actually really hard to implement. The reason being, well, we don't know exactly when I click them, right? If I'm on the receiving end of all of these keystrokes, I might see, WASD click, but I don't know exactly when those clicks were done, and as a result of that, I can't really replicate that state back on my own machine. So in theory, I could include the timestamps that I clicked everything, but then that still doesn't really make sense because as far as synchronization goes, between multiple computers, everyone's going to have slightly different timestamps, and it's just not going to work out. So let's go ahead and nix that strategy. This won't work. And what we'll do is we'll move on to strategy number 2, which is ideally going to be quite a bit better, which is actually going to be sending game state messages, right? So basically, for example, if I'm player 2, I can move to 100, 300. I can send this out to all the other clients, and all the other clients can apply this on their own machine. Now, of course, if they're applying this too slowly, this is going to be a pretty bad experience, but that's why I said we have to make everything pretty fast. And so another thing to note is that, depending on the type of message, we may be able to drop some of them. So if I'm going like 100, 300, and then I'm going 101, 300, and then 102, 300, maybe if one of the other clients drops this 101, 300 message, it's not so bad because they're going to get the 102, and then all of a sudden I'm back to the proper state that I should be in. That being said, if we're talking about like shooting a bullet, if another client doesn't understand that I've shot a bullet, that's quite bad because that bullet could have hit them, they might have died, and then all of a sudden now we're in an inconsistent state. So some messages do definitely need to be delivered, others are droppable. Okay, with that in mind, let's quickly touch upon peer-to-peer gaming, because this is something in theory that's always going to come up, right? If you can avoid having a centralized server, it may actually be quite useful because then you don't necessarily have one single bottleneck where all of the updates have to go through. So I guess the question is, is it actually worth doing this? And I would say maybe it is possible, but at the end of the day, if you have 1,000 people in a game sending messages to 1,000 other clients, that's probably too much. Now it is possible that, say, you've got a few different game servers, right, that all act as leaders and are all basically sending messages between clients. And that's possible too. But then what we could happen is we could get write conflicts, right? So if I write to one leader, someone else writes to another leader, and basically in my leader write, I'm saying I shoot you, and in your leader write, you're saying you shoot me. Well, who actually wins that? We could do some sort of weird conflict resolution, but then all of a sudden on my screen, it's going to look like I won that battle, and then 5 seconds later, I'm going to get a message telling me, hey, you're dead. And I'm going to be like, well, that sucked. I have no clue what happened. So ideally, you do probably want some single leader to actually order all of these writes. Cool. And then another question is, okay, well, if a client did go down, how can we actually store the game state somewhere so that we can restore that state on the client? Because, if we're just sending messages from one client to another, I guess the only way to actually restore state there would be for the client that went down to ask all of the other clients for their game state and then basically merge them together somehow, which is not ideal. And then the final thing is, another thing that's always going to be important with video games is stopping people from cheating, right? So if I'm just sending messages from my client to your client and there's no validation step in between there, I can basically say, hey, I just moved across the entire map. And you might say, oh, okay, that seems reasonable. Now, to be fair, you could do the validating on your individual client, but then we're doing a lot of duplicate work. It might be better to just centralize that entire process. Cool. So like I mentioned, if I'm moving from 100, 300 to 300, 300, that's just teleporting. That's not fair. I can't be moving around like that. I mean, in reality, I'm fast as fuck, but in the video game, we like to keep people honest. So what do we do? Well, we can actually go ahead and introduce a centralized game server, right? So the point of the game server is that it's basically storing a snapshot of the entirety of the game state. So it gets all of these incremental messages from all the clients of their own game state. So say I want to say I'm moving to 200, 200. Now all of a sudden the centralized game server is saying, okay, Jordan is at 200, 200. And not only does it do that, but it also is going to be responsible for delivering all of those messages to the interested parties. Okay, so what are the pros of an approach like this? Well, for starters, we now have much fewer active connections per client. If I'm playing the video game, I just have to connect to the game server. That's it. I don't have to connect to 1,000 other things, which is great. We can also perform some validation against cheating. Now in the diagram that I have here, if we're assuming that doing the validation against cheating takes a while, maybe we're running some sort of, like kind of simple regression model or something to realize if an individual player is cheating, we can actually pipe all of those updates into Kafka and then handle them on our anti-cheat server and then handle that downstream. If the anti-cheat server says, oh, player 2 is cheating, we can kick him from the game eventually, but maybe we'll have to take an extra 10 seconds to determine that. Another thing is that we can restore game state to failed clients. So like I mentioned, the entire point of the game server is basically to cache the existing version of the game state and also send out all of the messages that are incremental. So if we have a cached game state, what it means is that a client that goes down and comes back up can go to the game server and say, hey, I need that game state back, and the game server can actually respond with it. And then also another important thing is conflict resolution or message ordering. Because we're writing to one node, all of our writes that go through properly are going to be linearizable. So if I shoot you and you try and shoot me at the same time, only one of us is actually going to be staying alive. Cool, let's talk about restoring game state, because while I acted like this was trivial, in reality it probably isn't. The idea here is that, if I'm a client and I go down, I want to be able to get the entire game state back on it because I'm going to have lost that. It was probably in memory, and even if I did write it to disk, I'm going to have missed some updates since then, so I probably want to go ahead and ask the server for all of the updates since then. Now, in theory, you could probably read every single incremental update one at a time, but actually applying those would probably take a while. It would be a lot better if we could just get a snapshot of the actual game state itself. So, what is the problem of doing this directly from the game server? Well, think about this from an actual concurrent programming perspective now. If I am a client and I ask the game server for its game state, the game server now has to basically pause and not add any additional operations to the game state while it's copying that object to return back for me. And that's a problem. The reason being that during that time, every single other client is still playing the video game. So maybe it takes a second to copy that massive game state object and send it back to me. During that second, all of a sudden now the video game pauses because the game server can't basically process any more updates. It's grabbed a lock saying, hey, I'm not going to allow you to touch the game state. And so that would be bad. We don't want to stop the game from progressing. So what can we do instead? Well, perhaps rather than having to grab a lock right here to get the full state, and then this guy basically trying to do an update and having their operation blocked, what we can do instead is actually offload this entire snapshotting behavior to another server. So how do I propose we do that? Is this overkill? Very possibly, but I do think that if you have 1,000 people trying to update state at the same time, it is absolutely not a trivial operation to return a snapshot of it. Cool. So let's use a state machine replication tactic to actually create this snapshot server. So as in typical Jordan fashion, we're going to throw a Kafka queue in here. So we've got our game server. This guy is taking in all state updates. So for example, this could be like, hey, move my character. It's going to put all of those into Kafka, which is nice because now they're all ordered, right? They all have an offset number. And then we've got this snapshot server that is consuming from Kafka. So the nice thing about the snapshot server is that because all of these updates are getting buffered in Kafka, there's not really much pressure on the snapshot server to consume them super fast. If it has to pause for a second, that's okay. Then it can go back to consuming all of the updates from Kafka. So the snapshot server can go ahead and do that. And as it does, basically what ends up happening is that the reader can do two things, right? So let's say this guy went down and now he wants to basically do a select and subscribe, where the select is saying give me the snapshot and the subscribe is saying get me all new messages. What he could do is go over to the game server and say, hey, I'm listening to you again. Start sending me all the new incremental messages. And so the game server starts sending him messages. And so it sends him 22, right? Message with offset 22 because all these messages are ordered. We can order them because they're all going through one place. 22, 23, and 24. And so now the reader can say, oh, shoot, you know what? I need everything up to message 21 before I can apply these to my local state. And so what it's going to do is go to the snapshot server, say, hey, I would really like a snapshot at state number 21, and the snapshot server can go ahead and give it to that, right? If it's possible that the snapshot server doesn't actually have all of those messages processed yet, maybe it's only processed up to 19 for now, we can use something like a long pole to basically hang out over here, and then all of a sudden the snapshot server will give it a snapshot. If it's the case that the snapshot server has already processed, let's say, messages 22 and 23, that's totally fine too, because then we just won't process them on the reader over here from the game server, and we'll only process message number 24. So basically, we'll wait until we get a snapshot with an offset greater than or equal to the incoming messages offsets, and then from there we will, buffer all the incoming messages in memory and then apply their results right after that. Now, is it possible that there are so many messages from the game server in this very short period of time that we completely take down the reader? I guess in theory, yes, this is always something that is going to be plausible. But at the same time, I would think that as long as the snapshot server is reasonably fast, this shouldn't be too big of a concern. Cool. So hopefully that makes sense about how we do this kind of select and subscribe functionality, because we're actually going to be using this in a few different places throughout the video, which we'll get to in a little bit. Okay, next we're going to be talking about building fault tolerance. So of course, for their snapshot server, we've got Kafka for buffering messages, and it's fine if we need to pause for a second because those messages are going to be buffered in Kafka. However, that does actually have a couple of problems, meaning that there is more of a delay between when a message gets published from our game server and actually makes it to the snapshot server. And ideally, if we want basically a replica of our game server, we want that replica to be as up-to-date as possible. Additionally, having Kafka as another kind of middleman between the game server and the snapshot server just acts as another point of failure. So what can we actually do? Well, this time we can do a full legit state machine replication and talk about that a little bit. So in this case, the game server, as opposed to basically publishing messages through Kafka over to our Snapshot server, it can actually publish messages directly to the game server replica. This is what we call state machine replication. If you watch my video on building a fast stock exchange, same concept that they use for building their replicas out as well. I'll make that video again eventually, but for now you'll have to trust me. So gist is here that by using our state machine replication, we can imagine that basically any message that gets sent back to our users is also getting sent to our game server replica. It is possible that this guy may drop some messages, but if it does, then it probably means that other clients are going to be dropping them too. So we can have multiple game server replicas if we really needed to, but the point is this should hopefully keep it so that most of our messages are not getting lost. And if this guy were to go down, we can use something like Zookeeper to promote this guy over here. Cool. Okay, now we're actually going to be talking about networking a little bit and perhaps even some front-end optimizations to deal with this. So, like I mentioned, especially when it comes to certain interactions in the game, especially something like movement, I don't actually have to see all game messages. And it's useful for movement, right? Because movement is probably the message that gets sent to the game server the most, right? At all times, all players are moving. They're not necessarily shooting their gun, but they're certainly just moving around, and that's pretty important to understand. And so, if I am talking about movement in particular, right, if my character is going here to here to here, and we drop the middle packet, that's okay, because this is going to resolve itself when I receive the character's next location. So, unfortunately, as I also touched upon before, this doesn't work for all state messages, right? Not all of these things are kind of self-resolving. If I were to use an ability and that didn't get sent out to every other player, all of a sudden it's as if I didn't use that ability. That would be bad. If I shot a bullet and it didn't seem to everyone else like I shot that bullet, that would be bad. If the score didn't get updated, that would be bad. So there are certain messages that we don't want to be dropping, but there are others that we can drop. And so what you should start thinking about here is actually particular types of networking protocols, such as TCP and UDP. So for the messages that we can't drop, and for those that we need to send in order, right, like the score or my kill-death ratio, we should absolutely be using TCP. This is good also because it's going to ensure that the messages get there in order, that we're not overloading basically the network as we're sending packets out. And again, it's going to be useful for our state machine replication. At the same time, there are going to be certain messages that we're okay with dropping. Movement is the main one that I thought of, but I'm sure if you really think about it, there are probably plenty of others that you can throw in there. And so for these, we can actually use UDP. UDP is nice. It's going to be a little bit faster than TCP for a couple of reasons. The one being there's lower overhead to the actual message headers themselves. You don't have to wait for acknowledgements in order to ensure ordering, right? You just go ahead and send out messages as you please, which is great. And then also there's no congestion control. In TCP, we do flow control and congestion control, and I have a video devoted to this. But the gist is we don't really care if we're overloading the network. We're just going to send out packets and hope we don't. Cool. So the fact that we're dealing with UDP can actually make things a bit tricky. And even for TCP as well, if our server is particularly slow, it can make the game pretty choppy on the user side, right? If you think about actual modern gaming PCs these days, some of those monitors are able to update at 240 frames per second, and we have good graphics cards that can actually churn out that rate for lighter games like CSGO or Valorant or something like that. And so the question is, how do we actually stop our clients from having a pretty choppy experience because they're not receiving updates from the server as much, right? Even if you have a 10 ping, which is great, and you're hearing from the server 100 times a second, your monitor is probably updating more than that. And so what a tactic is that a lot of these games will actually use is something called interpolation. So interpolation is where we basically assume that for certain things like movement or maybe the movement of a bullet, that it is going to continue to travel in its current path until we hear otherwise from the server. And it's kind of game engines or physics engines that do this rendering. But the gist is, if I'm already moving in this direction and all of a sudden I don't hear from the server, my computer is still going to assume that I'm moving in this direction, and it's going to keep me moving that way. If you've ever played Rocket League, for example, and you're really lagging, what you'll sometimes see is the ball continues to move as if it's dropping normally, and then all of a sudden your screen flashes back and you realize that someone hit the ball and it's moving in a completely different direction. That would be a perfect example of interpolation. It's just more noticeable because you're experiencing really bad lag. Cool. So again, this is basically just predicting what the movement's going to be. Sometimes it's wrong. The more server updates you get, the less noticeable this is. Okay, so we've now kind of discussed the concept of having this centralized game server, where the game server is pretty much responsible for ensuring all of the state updates, caching the state, and sending it out and receiving it from users. And if we're being honest here, we have to update this state very often, right? Like, people are clicking keys constantly, people are doing things in these video games constantly, and we can easily overload the game server if there are 1,000 people on it. So what can we do instead? Well, of course, like we mentioned, leaderless replication is kind of out of the question here, or I should say multi-leader replication, because we can't really afford write conflicts. However, what we can do is actually partition out our game servers, right? So the question is, how should we partition it? Well, you may be thinking, oh, like, let's take each user ID that's playing in our video game and send it to one random partition. Well, that's not too great, because now all of a sudden, let's say I'm user 1, and I'm looking at user 2 and user 3 in game, and now all of a sudden, to know where their location is in game, I have to read a different partition for user 2 and a different partition for user 3. That's going to be too expensive. It would be a lot better if all of the people whose state I cared about were on my same partition, and same goes for all of the items. So what we should be really doing instead is partitioning by region. So if you imagine right over here that this is actually the coordinate plane of the game, because at the end of the day, all of these maps that you can play on are just 2D maps, what you can do is actually just shard them out by region of the coordinate plane. This actually is going to look very similar to the geo-sharding that we do with our indexes. Now, to be fair, I doubt we're going to need like tons of inner bounded boxes or anything. I bet probably sharding into 4 pieces or 9 pieces or something like that would be more than enough. But the gist is, you know, if I'm this guy over here and I only care about the items in this circle, right, because that's all my graphics card is capable of rendering, then it is pretty noticeable that I actually only have to read from R2. And same for this guy right here. He only has to read from R2, which is great because all the things he cares about are on that server. However, this is going to get a little bit more complicated when we have a player who is at the border of these region servers, right? So if I'm this guy over here, note that like kind of circle of influence that I care about. So how is this actually going to work? Because now all of a sudden I also care about all state updates from this region, which are on region 1. And previously I was only listening to the region 2 server. Now I'm close enough that I have to hear back from region 1. So let's go ahead and say something like this. You know, this guy is reaching out as it's moving. He's reaching out to the region 2 server to basically send it state updates. All of a sudden, he's too close to region 1. The region 2 server can say, hey, I actually don't cover this area. You've got to go back to the load balancer to figure out who does. He hits the load balancer in step 1. The load balancer says, oh, you actually want to listen to region 1 now as well. So what do? Well, now we have to get all of the existing state in region 1. How do we do that? We discussed this earlier. Not only do we subscribe to region 1, we also have to hit the region 1 snapshot server. And that's the only way that we're able to get the existing state. Otherwise, we would get all new state updates, but we would have no idea what the existing state is in this area over here, and that would be bad. So again, we do our same normal like select and subscribe process on the region 1 server. We then subscribe to all the region 1 updates, and now we're actually simultaneously listening for updates on 2 servers at the same time, both region 1 and region 2. Where things start to get really, really dicey is actually when we do cross-partition writes. So let's imagine the following situation. Me, as the absolute American sniper Chris Tile type that I am standing over here in region 1, and I'm about to snipe tech lead standing over here in region 2. At the same time, he happens to be close enough to the boundary between region 2 and region 1, but on the region 2 side, and he also shoots me. So the problem is, if we both shoot at the same time, my right goes to region 1, his right goes to region 2. Eventually, because we're listening to the state from both of these, we're going to see that we were shot, both of us, but we're not actually going to know who wins, because I'm also going to see that I shot him. So that's a problem, right? When we have 2 writes like this that could possibly conflict with one another across 2 different partitions, we basically need some method of actually performing ordering on them. And as we know, the only way to do this type of thing is to use something like a distributed lock. So fortunately, we have devoted an entire video on how to build distributed locking. And so you do know that the right way to do this is via Zookeeper. So that's the way that I will discuss it in this video. That being said, if you don't really care about having perfect fault tolerance, which may be the case here, maybe you'd be better off using Redis as a distributed lock, because that way you're reading and writing right to memory. And so yeah, sure, your distributed lock's not perfect, but it's probably going to save you a lot of latency, not having to do a bunch of two-phase commits within Zookeeper. And yeah, I would think this would be considerably faster. So do keep that in mind, but I am ultimately going to show Zookeeper in the final diagram. So yeah, what's the idea here? Well, you know, it's even possible that we could have a third guy over here on region 3, and he's also shooting at the both of us because, you know, maybe we can all see one another. We're all at the border of our 3 region servers. Regardless, we're all going to have to try and grab this lock for our particular region servers. And once we do, it is basically going to ensure that all of our writes are ordered, one of them wins, and the other people, you know, subsequently hear about that write, and their write is not allowed to proceed. Cool. Let us now talk about the last aspect of this video, which is going to be dynamic partitioning. So, as you can see, I've got like 7 steps on this diagram. And that's going to be a lot for me to go through, but we're going to try and do it as I begin to lose my voice here. So basically the question is, our game is progressing, right? And our zone that everyone can occupy gets smaller. So it's possible that that zone can actually be located in a single region server. And if not enough people have died yet, now all of a sudden maybe out of our 1,000 people, 100 have died, but everyone now again is located in a single region server. And that would be bad. Our region server can become overloaded. So how would we deal with something like this? Well, in the last 2 slides, I introduced this load balancer over here. So ideally, what we're going to have is a pretty smart load balancer that is doing the following. We've got some smart sort of load balancer, which I'll call the master server, which is basically listening from to Zookeeper. And Zookeeper is getting constant heartbeats from all of our region servers, saying how much load they're under, right? Maybe their CPU usage, their memory usage, something like that. And when it crosses a certain threshold, we can put that in Zookeeper, and the master server can actually read from it. You can just put a watch in Zookeeper, and that way the master server will hear when that entry is updated. Cool. So master server hears about it. What does it do in step 2? It actually goes back to Zookeeper and says, hey, I also happen to note that there's an idle server over here. I would like to go ahead and convert this thing to basically split the region 1 server in half to a region 1A server, and then the idle server will become the region 1B server. So the master server is then going to basically change the Zookeeper configuration. So it does that successfully. Now, all of a sudden, the idle server understands that it is the region 1B server. But here's the problem, is it has no state, right? This was just completely idle. It wasn't doing anything. We just have a few extra computers laying around specifically for this purpose in the event that servers get overloaded. So what does it do now? Well, it says, oh shoot, I've just become the region 1B server. What is the region 1A server that I'm getting this from? And once it hears from Zookeeper and figures that all out, what are we going to do again? We're going to use our existing snapshot and subscribe functionality. So that's reading from both the region 1 server as well as the region 1 snapshot server. And it is basically duplicating the exact state that the region 1 server had on it, because now all of a sudden we have all of the region 1B state on there because it's only half of what was on region 1. So now all of a sudden we are perfectly up to date and we're still subscribed to this region 1 server, getting all of its updates. Okay, once that subscription is complete, right, once we're caught up, we can go ahead and tell the region 1 server that, and all the region 1 server has to do is continue sending all of its messages over to this guy, and then, just like that, kick all of the clients that are actively connected to it that should now be on region 1B. Simple enough. What's going to happen now is basically this guy over here who was just kicked is going to reach back out to the master server, which effectively acts like a load balancer. The master server is going to say, hey, why don't you connect to the region 1B server now? And then all of a sudden this guy is going to start subscribing to the region 1B server, at which point he is good to go. It could be a select and subscribe as well, just in the event that there were multiple clients and multiple clients have been sending events to this guy in the meantime. But hopefully you get the point here of how we might be going about doing something like this. It's definitely not something easy to do, but it may actually be warranted if it's possible that one of these servers can get enough load on it. Okay, cool. Now just to quickly lay out all of our pieces that we've been discussing throughout this video. Basically, we've got our client over here on the left. The client is always going to be connecting via the master server to any of these region servers, and the reason it's doing that is because the master server is aware via Zookeeper over here of which server is which particular region and which one it should correspond to. And as a result of that, the first thing that we want to do whenever we're connecting to a region server is establish something like a WebSocket connection with it. The reason being that even though we are going to be sending a lot of UDP updates, at the end of the day, we have to send a lot of TCP ones as well. And it would be great if we could establish a persistent connection that doesn't require us sending headers over and over and over again. So WebSocket, at least to me, seems pretty ideal here. So we're using our WebSocket to basically say things like, hey, I shot a bullet, hey, my kill went up, something like that. And so the region 1 server is now all of a sudden communicating directly with our client via WebSocket, and additionally via UDP for those droppable updates, because ideally that is going to be faster. Cool. At the same time, the region 1 server is doing a couple things. It is using state machine replication over here to send messages to the region 1 backup server. It's also sending messages via Kafka to the region 1 snapshot server. And in addition, although I didn't really draw it out here, we might have an additional server that can be used for anti-cheat. Cool, hopefully that makes sense. Region 2 server will be doing exactly the same thing. We've got a backup, we've got a snapshot server. Additionally, we've got some passive master server, because at the end of the day, whenever we have one master server like this, it can always go down. This is pretty easy to keep up. The passive master server can just be doing the same exact thing, also listening to Zookeeper, having the same exact state, and if this guy were to ever be heartbeating to Zookeeper and then stops doing so, the passive master server can take over. Clients can read Zookeeper to realize that that's where the new master server lives. The last piece of this puzzle is actually going to be the distributed lock, which, like I mentioned, I want to live in Zookeeper. Stop it, ambulance, this is not cool. Like I mentioned, I want this to live in Zookeeper, just as client has to go ahead and grab the distributed lock when doing multi-partition writes, but other than that, if they're just writing to a single partition at a time, they can go ahead and avoid that distributed lock. We just need to have all those writes that are across multiple partitions be linearizable and blocking one another so we don't have write conflicts. Okay guys, actually not as long as I thought this would be, which is great because I am very tired. So I hope you enjoy the video, and I will see you in the next one.